There are many computer vision tasks in the analysis of neural images. Current tools predominantly design and train dedicated models for each of these tasks, despite there being large structural similarities between solutions. This dedicated model approach is not practical in many situations due to the large number of tasks and modalities involved and the limited availability of annotated datasets, implementation skills, or hardware. In this work, we introduced Neuralizer, a general-purpose neuroimaging model. Once trained, our model can perform unseen neuroimaging tasks in a single forward pass with no additional training. A special prompting setup allows the model to few-shot generalize to unseen tasks and image modalities. We set up our model so that Neuralizer uses a single model to solve all tasks on all neuroimaging data. The model has been exposed to a large range of tasks during training. As we see here, the model input and prediction are quite standard for image-to-image models. In this example, a modality transfer task. The input image is a T1 image and the output image is a T2 image. However, as the model is task agnostic, it doesn't know what we want it to do with the input. To tell the model what kind of output is desired, we condition it on the desired task with a context set of example input and output image pairs. In this case, T1 and T2 images from other patients. This example set is then fed through the model together with the input image to produce the prediction. No training or fine-tuning on the context set is required. The model adapts the task from the examples in a single forward task, even if the task has not been included in the training data. For the model, we use a fully convolutional architecture. The target input and context set are fed into the model as inputs. There, they are first processed by an embedding layer, shown here in gray, before being fed through multiple of our novel pairwise conv average blocks, shown in blue. We arrange 7 of these blocks in a multi-scale fashion using upsizing and downsizing layers in between to finally achieve the model output. One of the defining characteristics of our model is the need to allow for interaction between the target input and the context set representations. We model this interaction with the pairwise conv average blocks. Let's take a closer look at one of these blocks. Each pairwise conv average block receives the representation of the target image up here and the representation of the paired context set members down here. Each of these representations are first processed with a residual unit, where the units for the context set members share their weights. Then the representations of the target and context set members are pairwise concatenated, fusing their representations. A single 1x1 conv layer combines the representations, and its output is applied as an update to both the context representations and the target representation. To allow for a varying number of context set members, we average the updates on the target representation across the context set members. This way, we ensure data flow from any of the context set members to the target and vice versa. We train and evaluate Neuralizer on a diverse set of 8 neuroimaging tasks and 8 modalities. We use 2D brain slices in our experiment. We compare 3 separate models. First, a Neuralizer model trained on the training sections of all tasks and then evaluated on the respective test sets. We call this model Neuralizer Seen, as it has seen all tasks during training. Second, we take a Neuralizer model trained with a leave one out strategy, where we mask some of the tasks from training and evaluate only on these held out tasks during test time. We call this model Neuralizer Unseen, as it has never seen some of the tasks. Third, we compare to an ensemble of task-specific units where each unit has been trained on just a single task. This ensemble serves as a baseline in our experiments. The aggregate performs across all tasks by expressing it relative to the best performing model on each task. Here, we plot this relative performance on the y-axis in relation to the available dataset size on the x-axis. We have Neuralizer seen and unseen, our Neuralizer models that have seen some of the tasks during trainings and the one that has never seen the tasks it's been evaluated on, in blue and orange. And we have the baseline model, the ensemble of units, in gray. We see that the difference between the two Neuralizer models is small, showing that Neuralizer generalizes to tasks it has not seen during training with minimal loss in performance. Neuralizer outperforms the ensemble of task-specific baselines on small dataset sizes. As the size of the available data increases, the performance gap narrows, but it is still very significant at the largest context cell sizes supported by Neuralizer at 32 image pairs. Only when training the baseline on all available data, which for some tasks is thousands of patients, do the task-specific networks outperform Neuralizer. Note, however, that these baselines still need to be trained on each task, while Neuralizer generalizes to new tasks without any need for training or fine-tuning. To summarize, developing dedicated models for each task and dataset is often infeasible. This applies especially in neuroimage analysis, where many related tasks and a large pool of diverse image modalities exists. We propose Neuralizer, a general-purpose neuroimaging model. Neuralizer can perform any unseen neuroimaging task in a single forward pass with no additional training or fine-tuning. Neuralizer speeds up the use of deep learning on novel tasks and modalities due to not requiring training or fine-tuning and outperforms purpose-trained single-task networks in low data settings.